Good morning, everybody. This is Mr. Steele. I'm back one more time for the third part, hopefully the third and final part of the analysis review video created in 2019, helping you prepare for the new Unit 3 exam you'll be taking next week. So, as always, my hope is to work through each of the problems on the review, give you some feedback. I'm doing them all authentically. I haven't worked them out ahead of time, so this is my first time doing them, so you'll get some authentic feedback there, as well as to move forward. This morning, as you know, many of you know, I'm recovering from surgery. This morning I had the fun time of getting breakfast brought to me by Nathan and Simi. So that was a really great start to the day. So I'm hoping that'll carry me through and give me enough energy to work my way through the rest of this review, so that way it'll be totally posted before the unit's even over. Then I can finally begin my work on the test, and once that's done, finally, hopefully, I can actually work on the fun project we'll do in the last unit. Until that point, though, let's jump right in and continue working on the analysis review, at least one more time. Alrighty, so the first place we're going to begin is with the massive question, the last no calculator question of the review, that is on the fourth page of the piece. And this is question 16, and it features a table of values, but not a table of values in the traditional sense that we've seen lately, where it gives us f and g, two separate functions, as well as their derivatives. In this case, we've got a table with f, f prime, and f double prime all included. So kind of an interesting situation, but something to go through. So in here it tells us that we've got values of the twice differentiable function f of x. So that's an important thing to note because it tells us some information right off the bat. And it's worth kind of pointing that out here. It tells us first that f double prime is continuous, because twice differentiable means the second derivative is continuous. It also means that f prime is continuous, because the derivative of f prime is differentiable, or is continuous itself, which makes f prime differentiable, blah, 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 yeah. That also, of course, tells us that f is continuous. So basically, we're given all of that information straight off the bat. So we know all of f, f prime, and f double prime are continuous functions. And all but f double prime are for sure differentiable as well. It then also mentions that we've got the first and second derivatives. We already talked about that. And we're supposed to use the table to answer the questions. So in the last few years, it's typically been a last page kind of thing on the Unit 3 analysis exam. Maybe it will be, maybe it won't be, but I think this is a good opportunity to bridge together those differentiation skills from before alongside the actual work you're doing here, doing analysis with those derivatives. So let's jump into question A first. So question A says, let c of x equal f of x squared minus 3x. Is c increasing or decreasing at x equals 2? Well, I'm hoping that as soon as you see this phrase, c increasing or decreasing, your mind starts to think about what it means for c to be increasing or decreasing. What it means to me is we're going to need to figure out, is c prime of x greater than or equal to 0, or is c prime of x less than or equal to 0, specifically at x equals 2. In fact, I wouldn't even need to say x. I could actually be more precise and say c prime of 2. That's what we're looking for here. So in order to do this, we need to look at the derivative. So we're going to take the derivative of c of x equals f of x squared minus 3x. Now in differentiating this, there are a couple clues to lead you here, but this is a chain rule scenario. We've got some function composed of another, or as the second function inside of the first function. So if we want to, we could be super careful here. We could go c of u equals f of u, and we could do u equals the inside, x squared minus 3x. When you differentiate those pieces, we'll get f prime of u, and then u prime is equal to 2x minus 3. So this is one of those moments where you've got to be a little careful here. If we want to write c prime of x, the proper way to do that would be f prime of u, back substituting in the x squared minus 3x, times the derivative of u, which is 2x minus 3. Notice the parentheses. Parentheses have to be there, otherwise you'd be incorrect. So basically there's our derivative. So that was a good start. Now though, remember, we were interested in what was happening at specifically x equals 2. So let's compute what c prime of 2 is equal to. That's going to be f prime of 4 minus 6 is negative 2. This will then be 4 minus 3 is 1. So that's going to be just equal to f prime of negative 2. And f prime of negative 2 is equal to negative 3. So what we just saw is that c prime of 2 is less than 0, which implies c is decreasing. And then we should be specific at x equals 2. And again, our reasoning here, to explain our reasoning that was given by c prime of 2 is less than 0, Our answer, though, was decreasing. So again, pretty basic question, pretty basic differentiation using the chain rule, but obviously you have to recognize which derivative rule to use because there's no other real clues there, except for the fact that I named the function c. Okay, question B. Let p of x equal 3x f of x is the graph of p concave up or concave down at x equals 1. Well, if we're talking about concavity for p, we're going to be looking at p double prime sine. So in fact, I'll just write sine of p double prime. So in order to get there, we need to, of course, first calculate p prime. Looking at this function, I notice that we've got 3x times another function, which leads me to think that this is a product rule problem. Also, the function being named p sort of leads in that direction as well. P prime of x is going to be 3x prime times f of x plus 3x f prime of x. In simplifying this, we'll get 3f of x plus 3x f prime of x. So normally that would be where we'd stop. If we were talking about increasing or decreasing or something, we could literally stop right there. Fortunately, we're not. We are instead trying to figure out something about the concavity of p, which means we need to look at p double prime. So let's go differentiate one more time. So when we do the second derivative here, some of these terms are easier. The first one, for instance, 3f of x, that's just a scalar property. The derivative will be 3f prime of x. For the next one, though, this one is going to itself require the product rule as well. We had another product rule nestled in there. So this will be the derivative of 3x times f prime of x. Again, I'm not writing it out as carefully as I was before. Plus 3x times the derivative of f prime of x. And the derivative of f prime of x is the second derivative, f double prime of x. So this is our second derivative for what we're looking for. And we're interested in the second derivative at specifically x equals 1. So let's compute p double prime of 1. That'll be 3f prime of 1 plus 3f prime of 1. Interesting, there's two of those. Plus 3 times 1, or 3f double prime of x. Simplifying things, that's 3f prime of 1 plus 3f double prime of 1. Sorry, I made a mistake up there. Should have said 1. There we go. And now, oops, I combined like terms and I didn't even simplify. There were 3f prime 1 plus 3f prime 1 is 6x prime 1. Okay, so with those pieces in place, we now need to calculate their value. So 6f prime of 1, 6 times negative 7/8, geez, what was I thinking? Plus 3f double prime of 1, which is 2. So we've got, it looks like, negative 42 over 8 plus 6. And 6 is 48 over 8, which means this whole thing is equal to 6 over 8. Now 6 over 8, or 3/4, yeah, I'll simplify it. 3/4 is clearly positive. So we can say here that since p double prime of 1 is positive, p is concave up at x equals 1. And there we have our justification, as well as our correct answer of concave up. So again, in this case, you had to use the product rule to get there. You had to recognize that concavity leads us towards the second derivative. Needing the second derivative, had to do a nested product rule in the middle of everything. But we're able to get to our answer again with differentiation and quick analysis. Write the equation of the tangent line to f of x at the point where f of x equals 6. So as a heads up, this is not actually a Unit 3 question. This is just basically a quick follow-up to a question from the differentiation exam that people really struggled with in 2019. And I'm asking it because this sort of thing should appear somewhere else as well. So what this says is it wants to talk about the tangent line where f of x equals 6. In other words, that's where y equals 6. That's not saying find f of 6. It's very different. We're talking about where the y value equals 6. So this row, with all the f of x's, is where we're looking. So we have f of x equals 6. F of 1 equals 6 implies implies x equals 1. So we use the table to find it, kind of the same way we might use a graphing calculator to find the intersection and then use that x value. Now that we have 1, we need to consider what f prime of 1 is equal to. but we actually just used that on the previous problem too. It's negative 7/8. Then we want the tangent line, so y minus 6 equals negative 7/8 x minus 1. So there's our work, and you'll notice, by the way, as you're doing this, that this wasn't very hard. Again, it wasn't a Unit 3 question, but you'll notice that I gave you the distractor in here. So if you did this problem and you put that your answer was y minus 4 equals 8 quantity x minus 6, that means that you fell into the trap of reading and finding the tangent line where x equals 6, not where f of x equals 6. So you need to be able to tell the difference between that, and there's a very good chance somewhere on your Chapter 3 exam I will find a way to hold you accountable for. Okay, question D. Is there a value c with with c between 3 and 6 such that f of c equals 3? Explain your reasoning. So this phrase, is there a value c? That makes me, anytime you see that thing, it should make you think of IVT, MVT, maybe even EVT. So intermediate value theorem, mean value theorem, and extreme value theorem. So we're trying to find whether or not we can guarantee there's a particular value. So we need one of the value theorems. In this case, we're talking about f of c equaling 3. So that leads me to think, since it's just straight up f, we're probably going to use the intermediate value theorem, especially because the EVT is all about maxes and mins, and that's not what we're talking about here. And the mean value theorem involves slope. So I'm thinking it's not that one either. This looks like the intermediate value theorem. So next, let's go look at our table. So on 3 to 6. So on 3 to 6, we have our function going from negative 5 to 4. And I noticed that 3 definitely fits somewhere in the middle there. So I'm thinking this can work for the IVT. Remember though, to apply the IVT, you need two things. You need betweenness. And then think for a second, what's that other requirement you have to have for this value theorem? Yep, you need continuity. So we need to see if we can guarantee continuity. So in here, jumping in, if we're going to do our formal explanation, I'm going to start with the fact that the function f is twice differentiable. If the function f is twice differentiable, it means that f is both differentiable and continuous. So we start there. Since f is twice differentiable, I'm going to abbreviate differentiable for the sake of my sanity. Since f is twice differentiable, f is both differentiable and continuous. And I'll allow you to make that jump. You don't need to do the formal explanation of why. Let's see, since f is twice differentiable, f is both differentiable and continuous. And so we just established continuity. Let's hit betweenness. And in here, what do we got? H, or what do you call it? And negative 5 is less than 3 is less than 4. So, since we weren't given those values before, f of 3 is less than or equal to 3 is less than or equal to f of 6. So we've just established the betweenness as well. Notice, by the way, that I made this connection. I gave the values as well as the function values since they weren't given to us directly in the problem. They didn't say f of 3 equals negative 5. So from here, we just need to state the theorem. Thus, by the IVT, f of c equals 3 for some c. And I'll just put some 3 less than c less than 6. And there is our explanation. So again, this one isn't technically a Unit 3 problem, but it's important that you can tell the difference between the Unit 3 version that uses the mean value theorem and the IVT, because the IVT can still pop up and should pop up somehow on every single exam we do. Okay, question E. Is that right? It is E. E. Is there a value c with 3 to 6, between 3 and 6, such that f prime of c equals 3? Explain your reasoning. So now at first when you read this, you might think that this is literally the exact clone of the previous problem we just did. But the difference here is we're asking about f prime of c. And as soon as you see that little f prime of c up there, that should lead you to think about the mean value theorem. It doesn't mean it's not possible for it to be IVT. It could absolutely be the intermediate value theorem, although in this case I made it so it can't be. but seeing that prime leads you to it leads you to think that this is probably the mean value theorem, which involves the average rate of change and the derivative. So with the MVT, again thinking about requirements here, the things that you need are continuity and differentiability. Not even a betweenness, at least not right away. There's an equality, but whatever. Differentiability. Okay, so those two pieces. So is there a value C in there? So the first thing, well, we already said f is twice differentiable. So f is both differentiable and continuous. So we start with that statement to ensure that we've established the necessary conditions for the theorem to apply. And again, it's all given by just that little phrase that the twice differentiable function f. From here, when we're doing the mean value theorem, it's important to remember the mean value theorem, once you're guaranteed continuity and differentiability, involves guaranteeing there's a place where the average rate of change equals the derivative. So what we can do is we next find the average rate of change. Sorry, all these nights of not being able to sleep through the night are kind of getting to me. We'll have f of 6 minus f of 3 over 6 minus 3. That's going to be equal to f of 6 minus f of 3 all over 6 minus 3. It's equal to 9 over 3, which equals 3. So now at this moment, that wouldn't necessarily be anything special. We just found that the average rate of change is 3, or the slope of the secant line through those two endpoints would be 3. But the important thing here is that because we've guaranteed that the mean value theorem applies, we know that there's got to be a place where this equals f prime of c inside that interval. So to wrap this up, there's nothing else we have to do. We just have to state that it's a thing. So from here, we can then conclude, thus, by the mean value theorem, and again, I would accept MVT, but mean value theorem is nice to have formally sometimes. Thus, by the mean value theorem, f prime of c equals 3 for some c in 3 to 6. And there is our work. So again, this one, the things that led us to understand this was the mean value. Well, first of all, it was a value theorem question because it was asking about if there was a value c. From there, we talked about the fact that we could recognize it was mean value theorem because of the fact that we were requesting a particular derivative value. Not that we couldn't have used IVT potentially, but in this case it was based on that instead. And then from there we did the necessary conditions of differentiability and continuity. We found the average rate of change. Fortunately for us, it was equal to exactly what the problem asked us for. That was why they wrote the question. And then we were able to state, using the mean value theorem, that f prime of c has to equal 3, otherwise known as the average rate of change, for some c value between 3 and 6. So again, this one you can guarantee. This is 100% going to be asked on your test, at least one time. I think last year was literally on the first page. So be on the lookout for it. Know it's going to be there. There are 0 exceptions. This will 100% be on your test. AP exam as well, I think, but definitely on your test. Alrighty, f. So f then asks us to find the x value guaranteed by the mean value theorem for f of x on -2 to 6. So before we play along with that and do anything with it, I'm just going to take a quick little gander over here. I'm just going to remind ourselves that we already guaranteed ourselves that we can apply the mean value theorem at any closed interval in this particular function. Or at least we could theoretically apply it. So let's start there. F is twice differentiable, so f is both differentiable and continuous. That means that the mean value theorem applies. So good job us. Next, now that we know that it applies, we're on the interval -2 to 6. So that leads me to think we should compute the average rate of change. F of 6 minus f of -2 all over 6 minus a -2. Looking at our table, f of 6 minus f of -2. Let's see, did I do this right? Minus f of -2 all over 6 minus a -2. This gets me -7 over 8. So that's our average rate of change. Now remember, with the average rate of change, our goal is to figure out where in the function this is equal to the derivative f prime of x. We want to find the particular x value. That's the x value guaranteed by the mean value theorem, the place where the tangent line slope equals the secant line slope. So in looking here, we have to find a place from our table where f prime equals negative 7/8. Fortunately for us, we have such a place. It's right there at x equals 1. So here, from here, I don't know if you want to write a little more line of work, you could say negative 7/8 equals f prime of 1. So that implies the x value we're guaranteed is x equals 1. Is the guaranteed, that's not an abbreviation, I want it to be really badly, guaranteed value. So and again, last year I asked this, and it was a challenging question for students. Almost everyone saw mean value theorem and wrote this out, but then very few people were able to finish this problem off. So I think it's all about making sure that you remember what it is that the mean value theorem is looking for. If you're trying to find the value guaranteed by the mean value theorem, you want the x value. You want to know where it is that the slope occurs that we were guaranteed by the MVT. And again, this was on the test last year and the year before, so take that knowledge for what it is. Okay, this next brings us to question number 16G. This is one that I just had to adjust because I caught a mistake in it as I was doing the video. Hopefully that is corrected now. So the question begins by first offering us that d of x is equal to f of x minus 2x squared. And it then says if d of x has but one point of inflection for negative 3 to 7, not sure why I went into Old English, but whatever. It has but one point of inflection for negative 3 to 7. Write the equation of the tangent line to d of x at its point of inflection. So a couple things to talk about here. First and foremost, if we want there to be a POI on d, that would imply that we need d double prime to change signs. Actually, I'll write the word change. That's our first thing. We need to remember that. That is our formal definition of point of inflection. Point of inflection. D double prime changes signs. In this particular case, though, in our situation, because we have a twice differentiable function f of x, that means the second derivative f double prime of x has to be continuous as well. And since it's continuous, the only way that the function can change signs is if d double prime equals 0. So in our situation here, we can actually settle for finding where d double prime equals 0. Now some of you might already be looking down at the table and going, oh look, f double prime 0 right at 3. But that's not what the question asked. It's asking us about d, not f. If it was asking about f, yes, that'd be a really good candidate to be our point of inflection. Here though, we want to use d double prime. In order to get there though, first we need to get to d double prime. So first we need the first derivative, which will be f prime of x minus, it looks like, 4x. And then second, we'll take the second derivative. D double prime is going to be the second derivative of f minus 4. Now we just said a second ago that in our situation here we can settle for d double prime of x being equal to 0. So let's set this equal to 0 and see if we can find anything. So moving the constant 4 over, we get that the x value we want is when f double prime of that value equals 4. So next let's look at our table. Is there anywhere where f double prime equals 4? And the answer is yes, indeed. At x equals negative 2, f double prime is equal to 4. So that means that we've found our only potential place where a point of inflection could occur. And since we were on the interval from negative 3 to 7, which includes this entire thing, that must be the point of inflection for our function d. So basically what we've just shown is that d double prime of negative 2 equals 0. So d has a point of inflection at x equals negative 2. So given that, now our job is to just write the rest of the equation of the tangent line. So we've got a couple different things to go through. First, we need d of negative 2. So d of negative 2 is going to be f of negative 2 minus 2 times negative 2 squared. That's like too many 2's. F of negative 2 is 11, so we get 11 minus 8 equals 3. Next we need d prime of negative 2. We said earlier d prime was f prime minus 4 times x. So plugging in negative 2 there, we'll get negative 3 plus 8 is 5. And given those pieces, to wrap this puppy up, our tangent line is going to be y minus 3 equals, where's our slope, 5, quantity x minus a negative 2. So the tangent line part was really easy. It was actually the interesting part was figuring out where the point of inflection could be based on this table. So take that for what it is. think this is a really good question that does a lot of really good stuff, and it forces you to work with the table in a really unique way. So I'd say it's a pretty high-level question, but one that I think is very computable and very doable in a short testing-like time period. Okay, H. Is f prime increasing or decreasing at x equals 1? So this is one of those questions where it's super simple. It looks like uber simple and straightforward, but there's actually some kind of nuance underneath here. So it's asking us about f prime, but specifically whether f prime is increasing or decreasing. In a sense, you can think about it this way. If you want to know whether g is increasing, think about what you'd do. You would look at g prime and check whether it's greater than or equal to 0 or less than or equal to 0. So in other words, we'd look for g prime sign. So with f prime increasing or decreasing, what we need to look at here is we need to look at the sign. I'll do it this way. We need to look at the sign of f prime prime. In other words, that's just f double prime. So looking up at our table, if we're interested in the sign of f prime prime, otherwise f double prime, we can look and see that f double prime of 1 is equal to 2. And since that is greater than 0, that tells us that f prime is increasing at x equals 1. And our reason is because, well, we just saw it, because f double prime of 1 is positive. So in here, the reason I decided to toss this question in was just one of those things to remind you about these connections between everything. When you're asking about f prime increasing and decreasing, that really means you're asking about the concavity. That's what concavity is checking whether or not your first derivative or your initial rate of change is increasing or decreasing. So good question, I think good conceptual question to kind of think things through that wasn't very hard to execute with the table, but definitely involves some actual cognition as you are working through it. Okay, that brings us now to the calculator portion, which means we are only 10 problems away from finishing, or I'm only 10 problems away from finishing. You're probably working in smaller chunks than that. It's all good though. We want to work our way through here. Keep in mind these problems will be using the same analysis skills and the same problem solving that we've done before, but in this case we'll be using the graphing calculator to bridge some of the gaps, such as generating graphs of functions or finding intersections and solving equations. So to start things off, let's begin with question number 17. It says let f prime of x equal something complicated and crunchy. It says the average rate of change for f of x on 1 to 4 is 9.1495. Find the x value guaranteed by the mean value theorem for f of x on the interval from 1 to 4. So in here, by the way, in this question, technically we could probably just say that this last part isn't even necessary because they established the interval for us. But basically we're talking about a mean value theorem situation. And mean value theorem, assuming that we have a function f that is both continuous and differentiable, which we can't really tell from here, but we're going to assume it is based on the question, means that there's going to be a place where the average rate of change is equal to the instantaneous rate of change. In other words, average rate of change equals the derivative. So in our particular case here, we were told, first and foremost, that the average rate of change of f for 1 to 4 is 9.1495. Our job is to figure out for what x value on that interval is that equal to f prime of x. And of course that would be true for values between 1 and 4. So in order to do this, we need to keep in mind that we know the equation here. Like the equation of f prime of x is not 0, 2 to the x plus the natural log of x squared plus 5. And so we just need to figure out when is this true. Now normally we could just solve this equation, but since this is an equation involving such crunchy things, we need a calculator to be able to find it for us. We'll solve the equation by finding the intersection of their two graphs. So let's go in and take a look. Trusty calculator with 4 days left of my license, so I may need to work on this a little bit. So in here we're going to graph two different functions. This is from the last video I made, I think. We're going to graph first 9.1495. And second, we'll graph 2 to the x. It looks like plus the natural log of x squared plus 5. Okay, so from here, the other thing I'm going to do is it said that we were looking for a value between 1 and 4. So I'm just going to narrow the window so that we're looking between 1 and 4. Let's see what we got. Okay, so I see one single intersection point up there. That's a good thing. We barely made it in. Let's find that intersection with the Whittler button by choosing second trace. Oh, second trace, we'll choose option 5, intersection, enter, enter, enter. And, oh shoot, I can't bend down, but I can't see. 2.729. Let me make sure that was right. Try to make this bigger. No, I closed it. Shoot. This is gonna make it hard. Well, I guess it doesn't use up my window or my stuff. Pretty sure we found the right value. Okay, let's see here. The intersection, 2.728. 2.729, there it is. So, and again, keep in mind, what we just found was we let the calculator do the work for us, but we found the place where the derivative, f prime of x, was equal to the average rate of change. So in other words, if you wanted to check if you did this correctly, something you could do is you could check to see, does f prime of 2.729 equal 9.1495? So let's see really quickly. Let's do that, give it a shot. Like, we haven't done this for a while. So I'm going to store that value, x, as alpha a. And then I'm going to do math 8x. I'm going to do this at x equals a. So what we're doing is we're calculating the slope of the function. And then we'll do y2. I believe it was y2. Let's see if what did I just do? So, oh, we were looking for the slope. We didn't want to do that. Sorry, we were given the slope. Just kidding. We'll go alpha trace y2 of a. And the answer should be the value we were looking for, 9.1495. So in fact, we did get the value we were looking for from the mean value theorem. Good job, us. Okay, that brings us to question 18, which is an extended set of questions involving the same graph. So looking in here, we have g is known the derivative of g is given by g prime of x equals that complicated crunchy thing for values between -1 and 3. And then we're asked to do a bunch of analysis. So first and foremost, let's just take advantage of our situation here, and let's just go graph this thing and take a look at what we're dealing with for the moment. So this is x times 2 to the cosine 1.7x minus 3 all minus x. And then our window is supposed to go from -1 to 3. And again, as far as values, I don't know what's in here, so I'll just graph it as it is. That's hard to see. Let's make our y values a little more restrictive. Let's go -5 to 5. So again, I'm just trying to get a really nice picture of the function. That's still not quite there. Let's go -3 to 3. Okay, that's not bad. That's pretty good. In fact, I think that does a really nice job. So for the sake of using this, I think it'll be helpful just to have this picture handy. So, there it is. So our job is going to be using this picture and using the graphing calculator's capabilities to figure out the answers to all these questions. So let's see. So the first one, we want g to have a relative maximum. Explain our reasoning. So g has a relative maximum when, so I'll say because, g prime of x does a certain thing. Well, relative maxima on f are places where the function goes from increasing to decreasing, which means relative maximums for f prime are going to be places where the sign changes from positive to negative. So in here we're going to say that it's going to happen because g prime changes from plus to minus, from positive to negative. I'm just abbreviating those words. And then looking at our picture, we can pre-identify where those x values are going to be. So plus to minus, I see 1 happening, it looks like right there. I think that's at 0, but we can check just to make sure. I see a minimum right there, because that's where it's changing from negative to positive. And I do see a second one right over there. So we just need to find those two values. So let's go back into our calculator. Let's ask for help. I'll leave it right there because we can see it a little bit better. Make this a little bit larger. So let's see. Let's go. First, let me just trace it. I'm pretty sure 0 is 0. Yep. So one of those values is going to be x equals 0. For the other one, we'll find the second 0, or the other 0 we're looking for. I'm going to do that 0 between 2 and 2.9. And I'll guess that it occurs at 2.5. And it says that third zero is 2.689. 689. There we go. So two relative maxima for this particular function. And by the way, I might forget to do this, but I may also be able to use Desmos to show you the actual graph of the function based on this. We'll see if there's time at the end so I can actually show you this is all true. So stay tuned. Don't twist. Okay, for B, is G increasing or decreasing at x equals 2.5? So in this case, what we're trying to figure out is increasing or decreasing, which means we want to know the sign of G prime. So in looking up here, this is the graph of G prime of x. And 2.5, 1, 2.5 is, I think, somewhere right around here. So I'm expecting the answer to be positive. To make sure, though, we can go ask the calculator really fast and see what the value is. So G prime of 2.5 is 0.611. And the important thing about that value is that it's greater than 0. This tells us that G is increasing at x equals 2.5. And our reason would be because, exactly what we said earlier, G prime of 2.5 is greater than 0. So there is our work. And again, just using a quick picture of the graph, we could quickly identify what was happening here, and we could then go forward and justify our answer. Okay, C. On what intervals is G both concave down and increasing? So this is one of those favorite questions. A couple properties to look at here. See if we got this. So we've got a couple options here. So first and foremost, if we want G to be concave down, that means G prime needs to be decreasing. And second, if we want G to be increasing, that means we need G prime to be positive. So we're looking for all sections of the graph where G is both positive and decreasing. So positive and decreasing. So first of all, positive G prime occurs up here, negative G prime occurs down here. So we don't need any of that portion. So we're looking for the parts that are strictly above. So strictly above, strictly above. Now in our particular case, we want we want positive and decreasing. So looking at our stuff here, I'm seeing from right there to there, so something to 0. And then second, we'll go from there to there. And I believe that was it 2.689? Yep, 2.689. So fortunately, we've already found a couple of these values. We know a few of them, so we can work through a little bit faster. Of course, as always, to get the others, we need to use our graphing calculator. So in this case, we need the x-coordinates of the two maxima that we see in here, the two local maxima, excuse me. So second calculate, we'll choose option 4. So let's go right up there. Yay. So, normally I type in x values, but in this case it felt like a fun thing to do. So 1.895. I'll just label it here. We'll deal with the rest in a second. 1.895. The other one we said was 0, but the first relative maximum, go back to the Whittler button, go to option 4. We're going to go from -1 to 0, and we'll guess it occurs at -0.5. And it says it occurs at -0.604. I don't think there was any rounding. Should be sure. A 6 or 0? It's a 0. Yes. Okay, so given all that, we have everything labeled. As far as our intervals, we'd say that this is occurring on the intervals from -0.604 to 0, and, actually I'll just write two different intervals, and 1.895 to 2.689. So those are our two intervals. That's the direct answer to the question. As far as our reason why, even though it didn't ask, it'd be because f prime of x, sorry, it should be g prime of x, my apologies, because g prime of x is both positive and decreasing. So voila, we've now answered question 18C. And again, this is one of those questions where you're going to be for sure asked something like this. So just be on the lookout for it. Question 18D. Find the only point of inflection of G for 1 to 3. So first of all, I'm going to take advantage of the fact that we found a bunch of these values, which means I don't have to go back to the calculator every time maybe. So let's just start there. Okay, so there's what we have so far. This is where we stand. We're looking for a point of inflection of G, which we know there's lots of ways. We could say that that means G changes concavity. We could say that G double prime changes signs. Or we could say G prime changes between increasing and decreasing. So we're looking for any of those options. Keep in mind we were given G prime of X, so we can ignore those first two. Our focus is going to be using G prime, the tool that we're provided. When life gives you lemons, don't make beef stroganoff. So here we go. G prime changes between increasing and decreasing. So we're on the interval from 1 to 3. I only see one high point, and look at that. The one point of inflection on 1 to 3 is at X is approximately 1.895. Again, a value we'd already found for a previous problem, and our reason is because, and we can be really specific here. We can say it's because G prime changes. And we could say changes between increasing and decreasing, but in this case we can see from our picture, G prime changes from increasing to decreasing. So I might as well say from increasing to decreasing. And I'm sorry I'm abbreviating those words, I just really want to be done with this video. But there's our work, and again we didn't even need the calculator because we'd already done a previous problem on here, so efficiency. That brings us next to question E. At what x values does G have a horizontal tangent line? So this is one of those kind of loaded questions where it seems like it's a little bit complicated, but then if you just think about meaning, it can actually go really, really fast. So we want G to have a horizontal tangent line. That means we want a particular slope for G. What slope is this? What is the slope of a horizontal line? 0. Yeah, I think it's 0 as well. So the slope we're looking for is 0. So we're looking for anywhere where G prime of X is equal to 0. Good news is we've located two values where that happens automatically. Bad news is we need to find one more. That last one, although there is a possibility it's happening right there, maybe I need to investigate this one as well, but the other one we need to find are any other zeros that are on this interval. So G prime of X equals 0. I'll do my justification first. At, we'll have X equals, we'll do approximates here. Okay, what do we have? So let's check zeros. First thing I want to do is I want to check if there's a 0 at the end there. Oh, it didn't go to? Why didn't like -3? Negative 0.99999. It doesn't like that value either. This is weird. I wonder why it doesn't like that value. Okay, well let's try it this way. Y1 of -3. By the way, what I'm doing right here, I don't think I was narrating it very well. What I'm doing is I'm checking to see if y sub 1, or if the function is below the x-axis at -3, which would mean there's another 0 there. So notice that the value there is positive, which means it never actually crosses across. So basically we only have one more 0 that we need to find. So that was just a quick check. We found that there is no 0 over here, so I'll get rid of that. Instead we can say that those G prime equals 0 at x equals 0. We do need to find that third one. So we'll go to our calculation. We're going to calculate a 0 here. We want to find the one that's after 0. So we'll go from there to 2. We'll guess it happens at 1. It says it happens at 0.841. Technically it could also be 0. So it'll be at x equals 0. X approximately 0.841. And then our third value was that last one that we'd already found, 2.689. So in here again, some little vocabulary. A horizontal tangent line means that the slope has to be 0. That occurs at relative maxima or minima, as well as some slides that are out there. So we found all the zeros of our derivative graph on this function. We went from there. This is, by the way, also another way of asking for critical numbers. But know that this wouldn't necessarily get us all the critical numbers. It would just get us any critical number where the derivative was specifically 0 in this case. So keep that in mind. There is 18e. Okay, next, our final part of question 18 brings us to 18f. It says, let h of x equal g of x plus 4x. How many relative extrema does h have for -1 less than x less than 3? And once again, let me just throw all this stuff in here. Actually, I'm going to, oh, no, did I go all the way to the top? No. There we go. I just wanted to steal this really fast because it has all the labeled stuffs. Okay, so we got that ready just in case we need it. Okay, so h of x equals g of x plus 4x. We want to know how many extrema does h have on -1 to 3. So first of all, we don't know much about h, but let's do this first. h prime of x is equal to g prime of x plus 4. So from right there, if we're looking for relative extrema or potential relative extrema, we need to figure out when this is equal to 0. Would you agree? I would agree. It's the same thing though as asking, how often does g prime of x equal -4? So based on our picture here, we want to see how many intersections occur on this interval. Well, let's graph it on the calculator and see what happens. Let's see how many intersections there are. Interestingly enough, we don't even see that on there. The reason, of course, is that our window has been restricted and shrunk just such a way. So what I see here is that g prime never actually hits -4, which means g of x plus 4x never equals 0. So given that information, that means that h prime of x does not equal 0 for any values of x between -1 and 3. What that tells us is that there are no relative extrema. And again, not no relative extrema for g, but specifically no relative extrema for h on the interval that we were just looking at. So interesting question involving some interesting calculator skills. We basically could see that, hey, there's no actual intersection over the graph down there, which means that there's no actual places where this is true. So good job, us. Okay, that brings us to the final question of the review. This is another calculator question. In this case, though, they're talking about the second derivative of function f. So we're looking at the second derivative, and in fact, notice that they gave us f double prime of x. And it's valid, it says, for -2 to 2. And because I think this is an easy thing to miss, I'm going to make sure to underline the whole function because that -1 looks like something that I might actually overlook when I'm doing this myself. So there are a bunch of questions asking us stuff here. So let's just start things off by graphing the function, making sure that we've got that thing ready. Boom. ln x to the 4th plus 2 cosine x, and then it's all -1. So let's see what we got here. Let's go zoom 6. I know it's going to be only for -2 to 2. Okay, well, let's zoom in the window. -2 to 2, and let's go -5 to 5 to see if that does nice. There we go. Okay, so I might even zoom that in a little bit further. What the heck? Let's go -3 to 3. Yeah, you can kind of see. So basically our shape here, which I'm going to accentuate by copying and bringing over. Just want to make this a little bit bigger for the moment. As I look at it, you can kind of see it's tracing down, then it kind of lumps up for a little bit and then goes on from there. So it's basically just a really wide IW, or the Pringle guy's mustache, handlebar mustache. So in any event, there is our graph that we're looking at. Keep in mind though that unlike before, this isn't a graph of g prime or f prime, this is a graph of f double prime, which means in a sense we're looking at a graph of concavity, looking at a graph of the rate of change of this function f. So keep that in mind. So let's start with our first question here, 19a. On what interval is f concave down on that between -2 and 2? Well, concave down means lots of things, but for us, since we're given f double prime, we want to find where f double prime is negative. And I think it's pretty clear looking at this that f double prime is negative between that 0 and that 0. So basically, as far as our reasoning, we'll say that our reason it's going to be concave down is because f double prime of x is less than 0. And then our values we can find using our graphing calculator to identify those zeros. So let's go to the Whittler button, second trace. Oops. Go to the 0 feature. Let's go -2 to 0. Let's go -1. And it says our intersection is -1.184. And then from the other one, I have a feeling it's just a positive version of this guy. But just to be safe, let's do it carefully. 1.184 it is. So there is our interval. And again, we were looking for where the concavity was negative, where the function was concave down. Since we were given the second derivative, we looked for where the second derivative was negative itself. So everything below here gave us f double prime negative. So 19a in the books. Although I should probably just label this thing. Well, here. We'll do it on the next page. Okay, that brings us next to 19b. So it asks us how many points of inflection does this graph have here? -1.184, and this was 1.184. So we got our stuff labeled. So talking about points of inflection again, remember we said there's lots of different ways here, but keep in mind we want to look at points of inflection through the lens of the tools we have. So we have f double prime, so we want to think of points of inflection as places where f double prime changes signs. So looking at our picture here, I noticed that there are exactly two places where the f double prime, this thing that's been graphed, changes signs. The first one we looked at, and the second one we already looked at. So basically these 2 points are going to be our 2 points of inflection. So there are 2 points of inflection on the interval we're interested in. And if we're looking for a reason, even though it doesn't ask for one, we'll be better. We'll be the better person. We'll put one in there. There are 2 points of inflection on f between -2 and 2 because f double prime changes signs twice. So 2 points of inflection. So there we go. 19b, again, analyzing a second derivative graph, we use analytical approaches that involve the second derivative. Okay, finally, last question. I believe 65 is a blank page. It is known that f of 1.7 equals -16 and f prime of 1.7 equals 0. Does f have a relative maximum, relative minimum, or neither at x equals 1.7? So a couple things to point out here. Again, we'll throw our picture in one more time. So in our last question here, comes back to a familiar foe. So what are we told here? The f of 1.7 equals -16 doesn't mean anything. But if f of 1.7 equals 0, that implies to us that we have a critical number of the function f. So that means we're at a potential maximum or minimum. To make our decision, since we've got a graph of the second derivative, what we should use is the second derivative test. So let's determine what f double prime 1.7 is. Because if f double prime is positive, that means that we have a concave up situation, and if we're at the critical number, that would qualify us as a relative minimum. On the flip side, if f double prime is negative, we'd be concave down, and at our critical number, we would have a relative maximum. So it's all about the sign here. So 1.7 is, I think, right over here, but let's use the graphing calculator just to make sure. So we'll go Whittler it, we'll trace it at 1.7. So that is 1.09, it's definitely positive. So 1.09 ... which is positive. So from here, that means that we are concave up at a critical number, and concave up leads us to seeing a relative minimum. So we'll finish this off with a nice explanation. F has a relative, actually I'll write local, a local minimum at x equals 1.7, and our reason is basically because of the second derivative test, although we don't just say that, we actually cite the properties that are required for it. Because f prime of 1.7 equals 0, and f double prime of 1.7 is greater than 0. And with that, I believe this analysis video is complete. Thank you for watching. Hopefully this has been super informative and helpful for you. I've certainly I've certainly done it, but I definitely need to go rest a little bit, so I'm going to go do that. But again, I hope this has helped you in this unit, particularly in 2019 as you were dealing with me being gone the whole unit. So thanks for watching. Have a great day.